So here we're going to take a look at osmosis, and we're going to do so using an approach by Castian. Let's say we have a box, and we divide that box into two sides separated by a boundary that is made of palladium. And then on one side we put in H2 gas, and then the other side we have a mixture of H2 gas plus N2. So with palladium as the barrier between these two, uh, hydrogen can move in this direction, but nitrogen cannot move in the other way. So we have one-way transport. We have transport of, we have one type of transport. Hydrogen can move back or forth, but nitrogen is going to be stuck in this box on the right-hand side. So let's take what that means for chemical potential. So for equilibrium to be attained, the chemical potential of hydrogen gas in the pure side, that would be over on the left, must be equal to the chemical potential of hydrogen gas in the mixture over on the right. The chemical potential of nitrogen really makes no difference here. There's nothing to equilibrate it with because there's no nitrogen on this side. So there's the chemical potential of nitrogen over here is undefined. So we could just concern ourselves with the chemical potentials of hydrogen. So what do we know about the chemical potentials? We know that the chemical potential, there's a very sloppy mu of H2 for the pure stuff, will be equal to the chemical potential of the pure stuff at some given temperature plus a correction for the pressure. Let's call it RTLN, and then pressure of H2 for the pure case. And then by a similar token, the chemical potential of H2 in the mixture, which must be equal to this fellow on the left-hand side, will also be equal to the chemical potential of H2 of pure stuff at a given temperature, also equal to RTLN pH2. But here we're looking at the pressure of H2O in a mixture. So if the pressure of H2 on the right-hand side is equal to the concentration, the mole fraction of H2, multiplied by some total pressure PT, then we could put that in here, and this is what we get for the right-hand side, that the chemical potential of H2 in the mixture is equal to the chemical potential of the pure stuff at temperature plus RTLN, the total pressure, plus RTLN and the mole fraction XI. And then, of course, we can combine this to simply say that we have the chemical potential of H2 in a mixture is equal to the chemical potential of H2 of pure stuff at temperature and a reference pressure. So this is our total pressure there, plus some correction for the fact that we have an impure gas. So we have this form here. And in an earlier video, we talked about how we derive this RTLNX form using the ideal gas law. We're assuming here that the gases, which in this case probably do, approximate an ideal gas. So what does this mean? If X sub I is always less than 1, right, as it must be, because all the sum of all xi's must be equal to 1, so any individual component must be less than 1. That means the natural log of xi will always be less than 0, and this thing will always have a negative sign in front. And so that means that anytime you contaminate some pure stuff with X number of moles of some kind of material and you have this mole fraction xi, we will always reduce the chemical potential of that stuff in the mixture. So making mixtures means that we reduce the chemical potential relative to something that is pure. So now we have a thermodynamic argument for why H2 would migrate across that palladium barrier that we showed and spontaneously go into the H2 plus N2 mixture. By mixing nitrogen gas into the right-hand side, we've reduced the chemical potential of hydrogen gas, and if the chemical potential is lower here and we have a higher potential energy here, then stuff will flow down that chemical potential energy hill, and so H2 will migrate from left to right. How far? Well, there's a set of experiments that can probably be done at home. I'm not sure what kind of material you would use, but we can take a U-tube, and this is the way this is often shown in various online explanations of osmotic pressure. Let's say we fill a tube, and let's say it's open at both ends, and we fill it with water, but we're going to put a membrane here where that membrane does not allow, let's say, sugar, C6H12O6, which I think is glucose. So let's say that membrane does not allow glucose. So let's say it is impermeable to glucose. So there's that membrane, that barrier right there. And what we're going to do is we're going to add some C6H12O6 onto the left-hand side of this container. So we'll have H2 over here, H2O, but we'll also have a little bit of glucose. We'll just write that as Gl since that's all we've got the space for. So what's going to happen? We have decreased the chemical potential of water on the side by turning it into a mixture. So if you go back to the earlier parts of the video, we could play the same games, except instead of looking at the chemical potential of the pressure of H2O, we can look, or hydrogen gas, we can add an oxygen to it and talk about the partial pressure of H2O on this side. So by adding glucose, we have decreased its chemical potential. And that means water is going to flow how? You can pause the video for a moment and take a guess. Well, it should flow from right to left. Higher chemical potential here, where we've got the pure stuff, and then lower chemical potential over here, where we have H2O in some mixture. Well, if it flows in this direction, then you might imagine that the water will increase to some higher level. And it will. And if it does so, and this thing drops over here, because some of the material is shifted from right to left the way we've drawn that, then the difference in those heights will represent a difference in pressure. So if you look at the pressure acting on that membrane, we have less water over here hitting against the membrane on the right-hand side, and more water over here. And so that means the pressure on the left, the pressure over here, so the pressure in the mixture will be greater than the pressure over on the pure side, which is over on the right. And that can be taken, that difference can be calculated as the pressure due to the difference in the height of water after this level has subsided and this level has risen. And that weight of water, which is equal to that height distance there, that would be the so-called osmotic pressure. And why does this all matter? Well, there's a very interesting application where, let's say you increase the pressure of the system even further. We have greater pressure putting here on this left-hand side. Let's redraw our system. Let's take another U-shaped container over here. No, that's not going to work. We'll draw another one. And then we'll draw it this side so we don't make the same mistake. So let's say we have a higher pressure on the left. So we've got some osmotic pressure. So here's our membrane, a higher pressure over here, lower water level and a lower pressure here. So high pressure on the left, low pressure on the right. What we can do is we can insert a plunger. Let's say we have a piston that we put in over here, and then we attach that to a plunging mechanism and we increase the pressure. So over here, by this difference, that height of water, the weight of that water, defines the osmotic pressure. So let's just call it P sub OS. Well, we can take a pressure here where the pressure is greater than the osmotic pressure. And so what would that do? That would take water and force it back in this direction. Remember, we've got this contaminated mixture of glucose plus water, and then over here we just have pure water. So if we increase the pressure on the left-hand side, the natural tendency would be for water to move right to left. But if we increase the pressure greater than the osmotic value, then that'll push water from left to right. And if we push water from left to right, that's a way of purifying the system. We take this water that's contaminated with glucose. We don't want glucose in our water for whatever reason. And so we take the pressure on this side, we increase it to greater than osmotic pressure, and then we get pure water over here. So put a little star or a happy face. This is what we want. We want purified water. So if you have a so-called RO system, that is also known as reverse osmosis. And this is at least the theory in terms of how it's set up. You can have water contaminated with anything. It could be arsenic or nitrogen or uranium or anything else that you don't want in your water. So long as you can find a membrane that's impermeable to that stuff and you find a way of increasing the pressure so it's greater than the osmotic pressure that would be established based on an equilibrium between the chemical potentials of H2O on this side and H2O on that side, then you can run things in the opposite way. That's why it's called reverse osmosis. It's pushing things in the opposite direction that they would naturally go when we're trying to equilibrate chemical potentials without artificially affecting the pressure. So an RO system, or reverse osmosis, is a way of purifying water. Right? So there's an application of osmotic pressure and the ideas of osmosis and reverse osmosis.